In this lecture, we'll talk about healthcare data reuse, challenges and strategies. We can see from the blue that the content in this lecture is in sections 3.15 and 3.6 of the core content outline. Drilling down further into the outline, we can see that there are aspects of data and of technical approaches that enable sharing of data that will be covered in this lecture. The key topics for this lecture are the use and limitations of clinical data for patient care and other purposes, the flow of data in clinical systems from collection to storage to analysis, and use and challenges for identification and anonymization of patient data. Therefore, in this lecture, we'll cover the topics of the use and limitations of clinical data, the flow and analysis of clinical data, and identifiers and anonymization for clinical data. Let's start by talking about data integrity. Data integrity can actually refer to a number of other concepts. One term that is gaining a lot of currency is data provenance. Where does your data come from? How trustworthy is it? Other aspects of data integrity are completeness, so being certain that all the data is present, and correctness, that the data actually represents what happened in the real world of the clinical setting. We need completeness and correctness if we want to best reuse clinical data for other purposes. The core content outline also refers to mapping and manipulation of data. Data mapping to and from controlled vocabularies is discussed in lecture 3D 1-3, and data manipulation, such as retrieval from databases, is discussed in lecture 3A 1-2, and this includes things like querying, structured query language or SQL, and reporting. As all clinicians know, there are many types of clinical data and they're represented in different ways. Probably the most voluminous amount of data in clinical records is the narrative, that is text recorded by the clinician. Clinical data, though, also includes numerical measures such as blood pressure, temperature, laboratory values. It also includes coded data that is selected from a controlled terminology system. It also includes other types of textual data besides just the narrative reported by clinicians. There are also recorded signals, things like EKGs, EEGs, and so forth. And of course, there are pictures, everything from radiographs to photographs and other types of images. And then clinical data will often have metadata or information about the data, and this gives the context and detail, such as the electronic header information in a clinical note. One important subset of data is that which is coded. Coding of data is important, mainly from a remuneration standpoint, in that data clinical encounters must be coded in order for reimbursement to occur. Coding has historically been performed by one from the health information management field with the clinical coding specialist or CCS certification. Of course, there's a larger issue in informatics in terms of how we generate and use coded data for other purposes besides billing. And there's trade-offs for coding data. The standardization of language that makes data more precise versus the freedom of expression that clinicians want in their notes to be able to tell the patient's story. We also know that it takes a lot less time to narrate data than it does to code it in a structured form. There are other challenges as well. such as creating and maintaining coding systems and structuring coding systems so we capture the meaning of the data that we hope to get. One of the big challenges for data is its entry, and this is certainly a challenge in electronic records, but even in paper records, there are various challenges to data entry. We can think of the general categories of data entry: the free-form entry of data by historical methods of writing, of dictation, and more recently of typing. There is structured or menu-driven data entry that may be done by mouse clicking, by typing, or in the past by pens on mobile computers. Of course, we can use speech recognition for either free-form or structured data, or we can make use of scribes, who are people who enter data for physicians. Structured or menu-driven data entry has been around almost as long as there have been computers. There are reports of structured data entry systems dating back to 1970, and there are some more recent efforts. And of course, structured or menu-driven data entry can be done via a mouse, via a pen, and sometimes you point somewhere and then type in. Clearly, there's benefits to structured data entry. The data then becomes codified for easier retrieval and analysis, and it reduces ambiguity in the data if the language is used consistently. But in general, structured data entry takes more time to enter. It requires an exhaustive vocabulary, so we provide all the possibilities by which one might want to structure or code the data, and there requires dedication for using it by clinicians. One appealing method for structured data entry is speech recognition. The most common use of speech recognition in healthcare is for narration, where there's computer dictation of clinical notes. And even though early systems required 1-2 pause between each word, there are now continuous speech recognition systems that are a commercial reality. There are many established systems on the market, and they operate either on the front end, so they're used by the clinician to interactively enter the data, or they're used on the back end where recorded dictations are processed. Obviously, an advantage to front-end dictation systems is that instant availability of the dictated content and the interaction that the clinician has with it. And the problem with back-end systems then is that the editing task is transferred from the professional transcriptionist who just types what they hear back to the clinician author. There are both benefits and limitations of speech recognition. Modern speech recognition systems are very much improved over earlier ones, but there are still some challenges. One problem is that systems have an output lag behind the user input, and sometimes that can be distracting when one is speaking and viewing the text as it appears on the screen. And of course, speech recognition systems require an area that have a minimum of background noise and also where patient privacy can be protected. One study looked at the most common types of errors that speech systems make. These include enunciation errors that come from mispronunciation of words, dictionary errors when a word is not in the dictionary, suffix errors when there's misrecognition of appropriate tenses of a word, added or deleted words which sometimes don't match up to what the speaker has actually said, and then homonym errors when there is substitution of phonetically identical words. There was a recent systematic review of research studies of speech systems in medicine, and the reviewed studies were found to improve some aspects of productivity, such as faster turnaround time on reports, In looking at quality, human transcription was found to be slightly more accurate than speech, although that varied by setting and system. And aspects of systems design, the use of macros and templates, for example, improved turnaround time, accuracy, and completeness. There are some other well-known challenges for electronic data entry. One has been around pretty much since the widespread use of electronic health records, which is copy and paste. Many of the early systems just let clinicians copy and paste in unfettered ways. And early analyses found that it was used in up to 10 to 20% of charts. Some have wondered whether we need to rethink documentation in the electronic era. So perhaps instead of just copying and pasting massive amounts of patient data, being able to link to and annotate data so the note recognizes that there's data in other sources and we annotate it. And a number of organizations, including ECRI, have developed best practices for use of copy and paste. There's also concern whether EHRs may make it easier for fraud in terms of physicians stating things done that were not done. This has been an ongoing debate, and it still is not completely resolved. Another aspect of clinical data is its flow, and one of the places that clinical data flows is into data warehouses. This schematic shows some of the data that makes up clinical data, but it's important in that we recognize that data may originate from departmental systems such as radiology systems, pharmacy systems, lab systems, that flows into the EHR, and of course the clinician enters data directly into the EHR. Some of what's in the EHR may flow into a data warehouse that puts data into a system and a format that is easy to aggregate and query. And a data warehouse may not only have clinical data, but it also may have additional financial and administrative data. And of course, data may flow outside the boundary of an organization into regional and national systems, this of course being health information exchange. Another important type of information system in healthcare is registries. Registries can be thought of as a more limited form of an EHR. It can be a completely separate system from the EHR, or it can be an extract of data that is periodically refreshed. Registries are typically focused in what they cover. They are typically oriented to one or a small number of diseases, most often chronic diseases, and they're used for a variety of functions. They may be used for patient reports, such as tracking the status of monitored conditions. They may be used for exception reports, such as identifying outliers or patients who might be overdue for care. And then they may also be used for aggregate reports, such as how well is a care team in delivering the recommended care. Also important to data is data mining and knowledge discovery. Data mining, which is sometimes called knowledge discovery in databases or KDD, is the process where we discover patterns or knowledge in large databases. And of course, as growing amounts of clinical data accumulate in EHR and other systems, we look to the techniques of data mining to help us make predictions or to better understand what's happened in the clinical setting. A related term to data mining, and probably more commonly used now, is the term analytics, which has been defined as the extensive use of data, statistical and quantitative analysis, explanatory and predictive models, and fact-based management to drive decisions and actions. There are different levels of analytics and the related area of business intelligence. One approach to categorizing these separates them into 3 levels of descriptive, predictive, and prescriptive analytics. In descriptive analytics, we're basically looking at what our data shows. In predictive analytics, we're trying to predict what might happen based on past trends. And in prescriptive analytics, we want to use the data to optimize our systems and achieve the best possible outcomes. Let's define some other terms related to data mining. One term that we all hear a lot about is big data. We're in the era of big data. There are many definitions of big data. They usually revolve around some number of these V's. The most recent widely accepted definition comes from the National Institute for Standards and Technology. So, of course, big data is about volume, the sheer quantity of it, but it's not just about volume. It's velocity, so the speed by which the data comes at us. Variety, the different types of data, so in the case of medicine, text and images and waveforms and sounds and so forth. And variability, it comes at us in varying quantities and the different types of data and so forth. Another important term is machine learning, which is the branch of computer science that's focused on systems and algorithms that learn from the data. And there's much going on now with machine learning in terms of diagnosing images and other aspects in medicine. There's 2 broad categories of machine learning. There's supervised machine learning, where the machine learning takes place through the use of training data, and then the system learns from the training data and then uses new data that comes to it to make decisions. And then unsupervised machine learning, where there's no use of training data. Another term is text mining, where we apply data mining to unstructured textual data, oftentimes using techniques such as natural language processing. Some other terms whose definitions we should know related to data mining. One of these is data provenance. So what is the origin and trustworthiness of the data? For example, there might be different ways in a chart that we discern that a patient is taking a medication. It may be written in a note. It may be a prescription that was written. It may be a prescription that was filled. Data provenance just tells us where the data actually comes from and how believable it is. We can believe a filled prescription more than a progress note. Business intelligence is the use of data to obtain timely, valuable insights into business and clinical data, so the application of data mining. And another related term is precision medicine, which consists of prevention and treatment strategies that take individual variability, often the genome, into account for patients to diagnose and treat disease more precisely. We hear a lot about the data and electronic health records and other sources that we can do things with, such as predictive analytics, quality measurement, clinical research, and so forth. But there are challenges for using this data. One challenge is that the quality and accuracy of data in the electronic health record is not always as good as it could be, in part because quality and accuracy of that data is not a top priority for busy clinicians who just want to get their documentation done and move on to the next patient or go home for dinner. There's also large amounts of data. One study looked at pediatric ICU patients who generated an average of 1,348 information items per 24 hours. Another challenge is that patients get their care in different places. The data are not always able to be aggregated when we're doing any kind of analysis with it. A lot of data in the electronic health record is locked in text because we can process structured data elements much more accurately than text of patients. And it can just be difficult to combine data from different clinical locations, which have different workflows and so forth. And this one study from Broberg found that 5 leading academic medical centers that wanted to combine data for research and other purposes had difficulty doing so. We also want to be able to share data appropriately, to share data among different providers taking care of a patient, or to share data with those who do analysis or research. One of the issues is integration versus interfacing. In data integration, we try to merge the data from multiple sources into a single integrated whole, whereas in data interfacing, we try to interface the data and transform it so it can be integrated in real or virtual ways. Other technical issues are things like dealing with multiple identifiers and anonymization of the data. For many reasons, we may want to anonymize data. Obviously, in the care of patients, we don't, but we may want to use data for research purposes, quality measurement, etc. This has been a topic of great interest, especially in light of the insistence in the United States of not having a national health identifier. One of the leading researchers in this area has been LaTanya Sweeney, who noted that 87% of the US population could be uniquely identified by 5-digit zip code, gender, and date of birth. She also became famous for being able to identify Massachusetts Governor William Weld in a health insurance database of state employees, and she was able to purchase voter registration. I'll show this graphically in the next slide. And by linking zip code, gender, and date of birth to the de-identified medical database, was able to identify the medical record of Governor Weld. There's also issues of genomic data, which is perhaps the ultimate identifier in that our genome is unique. And of course, having access to this data can aid in the re-identification of patients who take part in clinical research studies. There are also challenges with Social Security numbers, and they can actually be predicted from public data. And another challenge is that when patients have multiple lab results, the pattern of the results of the lab results can actually facilitate re-identification of patients. Here's how Governor Weld was identified by LaTanya Sweeney. The left-hand circle shows the state health care database of all state employees with ethnicity, visit dates, diagnoses, and including zip code, date of birth, and gender. These data elements were also present in the voter registration rolls, and then that, of course, allowed linkage to the name and address, not to mention one's political views. Here are some additional suggested readings. There was a seminal paper published in JAMIA in 2007 that developed a framework for the so-called secondary use of health data. And more recently, a chapter on healthcare data analytics that I authored in the Health Informatics textbook edited by Hoyt and Yoshihashi.